Now we move into how to find the eigenvalues. So far, I've just been telling you how to verify, but not how to find them. Okay, so how do we find them? We want to find the number lambda, the scalar, so that a minus lambda I x equals 0 has a non-trivial solution. So from the invertible matrix theorem, this is equivalent to saying that I want to find all the lambdas where this makes it not invertible. So to be not invertible means the determinant is 0. I want the determinant of this, a minus lambda I, to be 0. So I'll be solving for the lambdas. All right, so this is my matrix A. So first I want to find a minus lambda I. So 2, 7, 7, 2 minus lambda times the identity matrix. So that gives me 2 minus lambda, 7, 7, and 2 minus lambda. All right, so now I'm going to find the determinant of this 2 by 2 matrix. So the determinant of 2 minus lambda, 7, 7, 2 minus lambda. You remember how to do this, right? This times this. So 2 minus lambda squared, subtract these two. So I want to set this equal to 0. So the determinant equal to 0 gives me the eigenvalues. So solving for the lambda, I get 2 minus lambda squared is equal to 49. Take the square root of both sides, so I get 2 minus lambda is equal to 7, or 2 minus lambda is equal to negative 7. So this will give me lambda is, oops, hold on, I'm doing too many things at once. So let's put this over here, so lambda, and subtract this, so I'd get negative 5. All right, let me do this, put this over here, so lambda is 9, and lambda is 5. So I get 2 eigenvalues for this matrix A. All right, so here I have another matrix. So I want to find a minus lambda I first. So that's going to be 3 minus lambda, negative 2, 1, negative 1 minus lambda. So I'm finding the determinant of this. So the determinant of a minus lambda I will equal 3 minus lambda, negative 1 minus lambda, plus a 2, right? Subtract a negative 2, setting this equal to 0. So this you must multiply out. It's been a while since you've done algebra, right? So if I multiply this out, and put them in descending order, I get to here, and I see that is not factorable, so you get to use your quadratic equation. B squared minus 4ac all over 2. So 2 plus or minus, then they give me root 8 all over 2. Okay, so there are 2 eigenvalues here for my matrix A. All right, so be careful. If I was doing this and I got a complex number in this radical, then that would mean there are no real eigenvalues, and we always want to have lambda be in the real numbers. So if you get a complex solution, you say there are none. All right, so here the eigenvalues of a triangular matrix are on the diagonal. So let's think about it. Triangular matrix, let me just do it with the 2 by 2 case because it's a little easier. So if I had zeros here, right, so these are the entries on the diagonal. If I did a minus lambda I would get this. And if I was to take the determinant of this matrix, this would give me a11 minus lambda times a22 minus lambda, subtract these two multiplied, which is 0. So I'm setting this equal to 0, right? So I get these two equal to 0. So I get the 1 lambda is equal to a11. Oops, and the other lambda is equal to a22. So these are the diagonal entries. So now let me come back to this equation here. So give me an example of a 2 by 2 matrix with one distinct eigenvalue. So I can put the eigenvalue of 2 on the diagonal. and that gives me where I can see that the eigenvalue would be 2. All right, so here we go. Yeah, so this is just saying the same thing, and I just gave it to you in a theorem, so it doesn't have to be just a 2 by 2. If I have an eigenvalue lambda, and that satisfies a minus lambda I x equals 0, and there are free variables, which means there's a non-trivial solution, then the entries on the diagonal give me the lambdas, the eigenvalues. So I can see here the eigenvalues would be -1, 1, and 2.